All right, welcome back. So, in the last video, we were talking about these kind of proportions, and we were talking about how the area underneath the curve, if we were to shade it and calculate that area, then that represents some probability, and that cutoff point represents some kind of percentile, right? Okay, so for right now, keep that in the back of your mind, because we'll use it here in just a second. But let's talk a little bit more about finding z-scores. Okay, so the idea here is actually not too crazy. It's not too crazy, I promise. But essentially what we're doing is we're just going to standardize things so we can have an easier time of comparing. So let's say that, let's say that I took the ACT, and let's say that I got a 28, okay? And I want to see how well I did compared to the overall population of other people who took the ACT. All right? Well, the ACT, let's say that the mean ACT score, so let's say that the population, and I'll do it in a different color here. Let's say that the population, let's say they scored 26, okay? Now already I can say that, well, I did better. I did better than, the average. Okay, I'm above average in some way. But we need one more piece of information. And that piece of information is the standard deviation of our population. Okay, so in this case, scores of ATC, ACT scores, rather. And let's say, I'm just guessing here, let's say that the average score deviates away from that mean by, let's say, 5 points. Okay, now this is all you need. This is all you need to calculate a z-score, okay? And remember, or recall that a z-score just tells you how many standard deviations you are away from the mean, all right? So, how do we find that z-score? Well, the first step is to subtract our score and subtract away the mean, okay? And then after that, you just divide by the standard deviation. Okay, as simple as that. So let me show you what that actually looks like. So my ACT score was 28. Okay, and I'm comparing myself to the rest of the people that took it. So that would be minus 26. Okay, and then we're just going to divide. We're going to divide by 5. Okay, so we have, I'll write this in green too. We have our value, x. We're just calling it x. We could call it anything, but we'll just call it x for now. And then we're subtracting away the mean, so that's mu. All right, and then we're dividing by sigma. Easy enough, right? Okay, so let me get my calculator out here. Some of this I can do in my head. So 28 minus 26, that's 2. All right, and then 2 divided by 5. Now, in stats and in this class, let's just work out fractions. Let's work out fractions. So instead of keeping it 2 over 5, we'll say this is 0.4. Okay, and since 2 decimal places, we'll say 0.40. Okay. All right. So that's easy enough. But what does this tell me? Well, this tells me that I was above the mean. I was 0.4 standard deviations above the mean. Okay. Well, this is now an easier way of sort of saying, okay, I did better. I did better than the average, but by how much did I do better? In this case, I did, well, I'm decently better. I'm 0.4 standard deviations away. And in the future, in another video here, I'll kind of tell you how we can calculate what percentile I'm in. Okay, so that's easy enough. All right, but here is the formula for z-score. And just for a clarification, I'm sorry that I could be a little bit more specific here, but this is for a sample, and we know it's for a sample because we have x bar here, so that's the sample mean, and we have s here, that's the sample standard deviation. I'm not sure. These aren't my slides, so I do apologize for this. But the formula for the population, it's the same thing, just different different values or different symbols. So it's still z, and it's still x. So that just represents what our score was, whatever it was, whatever we're measuring. And instead of x bar, since we're working with population, it's mu. And instead of s, since we're working with the population, it's sigma. Now, they both represent the same thing, so no big deal there. Just slightly different terminology. Okay, so that is the formula for that. Write that down if you're making a formula sheet. If you're not, then I recommend you do, because we've got a lot of stuff that we've done so far. But let me give you another example here, because that SAT or ACT or whatever, that was fine. That was fine. But we can be a little bit more specific with it. So here's an example. Okay, so you're a wildlife biologist assisting Jane Goodall, and you are on an expedition recording the heights of chimpanzees. Okay, so Jane goes out and she collects 100 chimps. So a decent sample size, right? We don't know what the distribution of those 100 chimps look like, but we do know that the mean is 48 inches, and of those 100 chimps, the average deviation away from the mean, the standard deviation, was 5.5. Okay, so you split up and you go find 5 other monkeys or chimps, and your job is to figure out how many standard deviations away your chimps are from Jane's. Okay, so it's as easy as that, and we'll actually just get into it. So I've got all the information here that you need. We just need to do a little bit of algebra. Okay, so here's the data. We've got the chimp names. So we've got Donkey, Diddy, Funky, Cranky, and Swanky. These are all characters from the Nintendo series Donkey Kong. All right. So these are real names, sort of. Okay, and then we have the height here. We have the height in inches. And then we have our formula for the z-score. We have our sample mean that Jane got and our sample standard deviation that she also calculated for us. So we don't really have to do any major calculations here, thank the Lord, because that would be unfair. All we need to do is figure out the z-score for each of these chimps, each of these monkeys. Okay. Now, I'm not a primatologist, so I really don't know what the difference is between a chimpanzee and like a monkey. I assume that it's a rectangle square kind of situation, but anyway, trying to keep this class like entertaining. Okay, so we've got Donkey Kong here, and I'll do the first 2 because I don't have enough room to do everyone. But the process you'll see is the same. So what I'll do is what I need to do. Just follow this equation. Okay, so z equals, all right, x 60. All right, and let me do some nice color organization here, color coding, where, all right, so just so you can kind of see where I'm getting everything. Okay, so then all we want to do is minus 48. Okay, and then divided by, divided by 5.5. Okay, and then I'll just get out the old calculator here. I'm using my phone as a calculator. We don't need anything special. So 60. Oops. Okay, so 60 minus 48 is 12. Okay, divided by 5.5. Let me do it in this color. Okay, so that equals 2.181. So we're not going to round. We'll just do 2 decimal places, 2 decimal points. That's fine. Okay, so that's it. Whoa, that's it. Whoa, 2.18. 2.18. Okay. Let's do the next one. Let's do Diddy. Let's do Diddy Kong. Okay. So same deal, right? Z, and let me draw a line here because that kind of looks like a 2. All we need to do is take 30, all right? Wrong color. Minus 48 divided by 5.5. Oops, 5.5. All right, So the only thing that changed here was this value. This value. Everything else is the same. Everything else is the same. So it's really not too bad. Okay, now this is weird, right? We're going to have a negative value. Well, that's fine. That is fine. All this is telling us is that it's going to be below the mean. It's going to be below the mean. So 30 minus 48, that's a negative 18. All right. And then divide that by 5.5. All right, and that equals negative 272. Okay, so we'll just leave it as that, negative 3.27. Negative 3.27. Okay, and then I'm just going to, on my calculator, and I encourage you to do it too, let's just do the rest. I'm not going to write it down because the process is the same. So we're doing 45 minus 48. It's negative 3, and then divide that by 5.5. Okay, so we've got negative 0.545. So we'll round that up to 5.5. Sorry, negative 0.55. Okay, and then 50 minus 48, that's 2. 2 divided by 5.5 is 0.363, so 0.36. Okay, and then the last one. Okay, here's an interesting one, and I'll actually write this one out too, so you can see that nothing funky is going on. Okay, so well, I guess not for Funky Kong, but for Swanky, notice that his height and the height of our sample, the height of Jane's sample that we're comparing, is the same. So what does that math look like? Well, I'll show you. So for Swanky, I'll write it up here. Swanky. I'll do it all in one color. It's 48 minus 48 divided by 5.5. What is 48 minus 48? Well, that's 0 over 5.5. 0 divided by 5.5 is nil. Big old goose egg, right? It is 0. So Swanky here is 0 standard deviations away from the mean. All right, so let's look at each individual one real quick. Okay, so Donkey Kong is 2.18 standard deviations above the mean of Jane's sample, right? So on average, when we're comparing Jane's sample to this one sample, this one observation here, this observation, Donkey, is 2.18 standard deviations away. Okay, Diddy here is Diddy here is the opposite, right? Diddy here is negative 3.27 standard deviations below the mean. Okay. Funky here is negative 0.55 standard deviations from the mean. Cranky, same deal, 0.36 above the mean. And Swanky is the mean. Swanky is 0 standard deviations away from the mean. Sorry, bit of a gap there. Okay, so what does this tell us? Well, this tells us just absolutely, sorry, not absolutely, this tells us relatively how our observations, how our sample compares to Jane's sample. Okay, all right. But how do we know that any of these are like special? Okay, well, if we recall, let's see, one standard deviation, and there will be more info on this in just a second, but one standard deviation, the data that is contained within one standard deviation makes up, I'll do it like this too. So one SD makes up 68% of the data, and I'm basing that on this picture here. Okay, so we see that within one standard deviation, 0.34 plus 0.34, that makes up 68% of the data. If we go one more out, if we say, okay, within 2 standard deviations makes up the sum of all these values here, which is 95. And then we can see as we go further and further out that we start to incorporate more and more of the data. Now, don't worry yourselves with those proportions just yet. In fact, I'll just erase it because it's not important now. But here's the take home. Here's the take home. And I'll write it over here on this new slide here. If, I don't know why. Okay. If a z-score falls, actually, instead of falls, let's just make sure that we won't be dilly-dallying here. Well, if a z-score is larger than 3 or smaller than -3, then the data point, whatever we're looking at, is considered an outlier. Okay, so now, and I'll make sure that we get this to larger, smaller. We'll do this whole thing. Okay, so what this is saying is that if we get a z-score from some data point, and that z-score is bigger than 3 standard deviations away from the mean, or smaller than 3 standard deviations away from the mean. I just sort of said the same thing, but I meant to say 2 different things. So if we get a z-score that's above 3, okay, so 3 or larger, we'll say, then that's considered an outlier, so 3 standard deviations above the mean. Or if we get a z-score that is -3 or smaller, then that is -3 standard deviations below the mean. And that is good enough criteria for us to consider that that data point is an outlier. Okay, so now we kind of have 2 different ways of calculating an outlier. One of them is based on, this z-score situation, and we also have that interquartile range times 1.5 plus or minus Q1 or Q3 respectively, right? It's telling us the same thing. It's telling us the same thing, just in a slightly different way. They might not always agree. And it's okay if they don't, okay? Because they're only suggesting. So instead of saying like an outlier in this case, what I really mean here as an outlier, I really just mean something that is unlikely, odd, or unexpected. Oops. And let me go back to this picture here. Way back over here, just to kind of explain what I mean. Okay, so everything that is within this region here is all good, right? This makes up, this region. Okay. This makes up a significant chunk of our data. And we would say that, it's pretty likely that if we were to go out again and get one more data point, that it's pretty likely that that data point would fall somewhere here close to the mean. And then it's even more likely the more that we include, and then the more that we include, right, the more likely that thing becomes, whatever we're measuring, right? But if we were to take each chunk at a time, so the likelihood, I've got a pretty good chance of selecting something that falls around the mean. But then if I go out and say, okay, what about this area here? Well, it's less likely. And it's even less likely that I get a data point that falls somewhere in this range, okay? But it's still, for whatever reason, statisticians have decided that it's still cool, that it's still, likely enough to where I can still randomly choose it, okay? But anything that shows up beyond here, any data point that is made up over here or over here, anything that's more than 3 standard deviations away from the mean in either direction, is considered very unlikely, okay? Very unlikely. Now, if we were to zoom in here, way zoom in, And if we were to say, well, what if I fall right here and right here? Oh, wait, actually, let me permanently draw that. Well, what's the difference between grabbing something that's right here? See, that's like way too big. What about something that shows up right here and beyond versus right here and beyond? Okay, that's a great question. That's a great question. There's really no... There's no reason, right? That minutely small difference is, we just don't care about it, right? We care more so about the large picture here, right? Okay, so just to kind of recap, pretty much anything that falls within here is expected, but then anything that shows up way out here or way out here and beyond is unexpected, right? There's a less, the probability of selecting something that is out there is much less than it is selecting it here. Okay, so with that, let's go back to our example, and I'll erase this just so we don't really need to worry about that just yet. But which one of these values, which one of these chimpanzees here is considered an outlier based on that criteria of being either larger than 3 or less than -3? Okay, well, Donkey Kong here is 2.18 standard deviations away from the mean, or larger than the mean. Diddy here, okay, Diddy is less than -3, right? So he is considered an outlier. He is considered an outlier. Diddy here. What about Funky? Funky is within the range, so that's good. Cranky and Swanky, they're also good, right? So our only outlier here is Diddy Kong. And he is, by just barely, by 0.27, he's considered an outlier, which is fine. Still an outlier nonetheless, but he is -3.27 standard deviations below the mean. Okay, below the mean, and is considered an outlier. Okay, so I'll call it here. But just as a recap, this is what we're doing, right? We're trying to really figure out how our sample compares to another sample, and how our sample, are there any outliers in our sample compared to that other sample that we have right here? Okay, and that is that. So I will see ya here in just 1 second.